Okay, everyone, we're going to make a start. It's 10 after 11. Professor Allen is at an earthquake early warning conference. It's right here on campus, but he is dealing with the lieutenant governor and some state senators and lots of media and things like that, so he can't be here today. So I will be giving the second half of the Hayward scenario lecture in his stead. I'm going to fix the lights. I don't know which button to push, but can everyone hear me okay? Yeah? Okay. Okay, great. So first off, before we get started, I've got a couple of announcements. First, like I already said, Professor Allen is at an earthquake early warning conference and can't be here. He is, in case you didn't know, he's the director of the Berkeley Seismological Lab. He's also more or less in charge of Berkeley's contribution to California's statewide early warning system. So yeah, he couldn't be here to teach because of that. So we sent out an email over BSpace. If you did not receive the email, you should email either me, I'm William, Cheng, or Avinash, one of the three GSIs, and let us know that you didn't receive the email. Or you can just stick around after class and we'll write down your information. You have to be enrolled in the class to get the BSpace email, and it will come through the email address that you gave the registrar when you signed up as a student. Yes? You sign up on the BSpace site. So there's I think there's a tab on the left side that says section info. Is that, you see it? Okay, great. So the content of the email was to sign up for a GSI, to sign up for a section. This class has no official section, so you're not required to go to this section time that's listed. Those are simply the office hours of the three GSIs. So you want to make sure that you sign up for a GSI whose office hours you can attend. If you can't attend their office hours, then you might have trouble getting in touch with us. So the idea is that you are welcome to go to any GSI's office hours, even if they're not the one you signed up for, just if one of them is more convenient at a given time. So that's that. You should sign up as soon as possible. Are there any questions about that? No? Okay. There were two earthquakes yesterday. Did anyone feel them? There was one that was an aftershock for the Napa quake. You felt it? Yeah. Cool. So there was an aftershock for the Napa earthquake that happened, I've forgotten the time, but yesterday when most people were asleep. There was another one, magnitude 2.9, that happened down basically right underneath Stanford. In case you didn't know, we are right on a fault, and they are more or less right on a fault too, so they didn't get out of that one either. So if you felt it, or even if you didn't, you should go to the USGS website and fill out the Did You Feel It form. Has anyone here done that before? USGS, did you feel it? Okay, I'm going to quickly, hopefully this works on this computer. Right. Okay, so this is the USGS, earthquakes.usgs.gov. Just shows you a map of where earthquakes have happened in the last week. So this is the Bay Area. I've already zoomed into it. These yellow dots here, those are earthquakes that have happened in the last week. The orange dots are ones that have happened in the last day. And if there were any that happened in the last hour, they would be red. And the size of the dot corresponds to the magnitude of the earthquake. So in the last day, there was this guy that is one of the aftershocks for the South Napa earthquake. If you click on the dot, it gives you a little bit of information down in the bottom left corner. This little blue square that says, Did you feel it? For is people went into the USGS website and recorded that they felt this earthquake. So yeah, when you click on this, I've already done it, so I'm just going to move over a tab. You get to a summary of the earthquake, which shows you a map of where the earthquake was. And if you click on this, Did you feel it? It lists responses of people who felt the earthquake in different zip codes. And the color of each of these zip codes corresponds to how strong the shaking was at their location. So this is interesting to go look at as a person who may have felt or didn't feel an earthquake. But this is also very helpful for the USGS because it allows the USGS to try to figure out, if an earthquake happens here, why did people feel it in this zip code and not this zip code? How is the distribution of responses? What is that telling us about the geology and the efficiency with which earthquake energy is radiating away from the source? So it's very helpful for USGS if you go and log this information for them. So no one felt this one in Berkeley, apparently, or at least no one reported that they felt it. And this is the 2.9 that happened more or less under Stanford. And this is the Did You Feel It map for that. This one happened at 8:20 at night. So more people were awake, so they felt it and filled it out. Berkeley's not on the map, but no one in East Bay seems to have felt it. So if you felt it, you were either really lucky or you might want to move. Okay, great. So that's all I have on those two earthquakes. If you felt them, congratulations. If you didn't, there will be more opportunities. Great. So I have some liquefaction videos. I'm going to go first to the slide that I think we ended with last time. This is this is a map showing likely freeway closures in the event of a magnitude 7 earthquake on the Hayward Fault. This red line is the extent of rupture, and these heavy black lines are places in the roadway infrastructure that we expect have a high probability of being closed after this earthquake. And what was the reason that we came up with for why these might be closed? Soft soils, yeah, liquefaction, soft soils that amplify the shaking. So I decided, I have a bad habit of going to YouTube and looking up interesting videos, particularly for this class. So I'm going to go show some interesting videos. I hope everyone's okay with that. Good. Extreme soil liquefaction. So, there's audio for this. I don't know how to plug in the audio in this classroom. Here we go. Okay, so this is a construction site. This is not during an earthquake, but you're going to see this fellow right here jump up and down, and the ground is going to behave in a way that could be a little bit alarming to you. Yeah, so that looks like solid ground, right? But clearly, if your building is on that, it's heavy enough that it might, they say some sort of vulgar things. You're in college, but I'm not sure I should play in class anyway. So I'm not sure that if your building was on something like this, I'm not sure that you would want to be in it. So that's the first video. That's what it looks like. And it's interesting, right? You see these cracks on the ground, you see these little pebbles. It looks dry. It looks like some soil that you would just walk on if you went out to the woods, but it certainly is not behaving like it at all. Okay, so this is an experiment that's being done. So there's a box here, and there's some sort of beam that's resting on sand. This sand is saturated with water, but the water is not above the level of the sand, at least at this point. And it's sitting on a table that's going to start vibrating. And the vibration is so fast that you won't be able to see it vibrating, but you will definitely be able to see the effects of the vibration of that table. So here goes. Yeah. Okay, so that's what happens to buildings that are built on saturated sediments when an earthquake starts to shake the soil. You would not want to be in a building if this were the cornerstone of the building, right? So I have tons and tons of these videos. Perhaps I ought to stop showing them. Yeah. So the question is, why do they build stuff on saturated soil? That's a really good question. I think part of the reason is that they don't know. So the soil is saturated virtually all the way to the top. In the case of building failure, it's not always saturated all the way to the top, so you can't see that it's saturated with soil until it gets shaken. But also, if you have something that's by the coast, it's inevitably going to be on saturated sediment. So if you want to build a port, you're going to have a really hard time putting it on something that's not saturated. Yeah. It's soil that has lots of water in it. So it's not dry, it's wet. But it's not so wet that it's like walking through mud. It's just got lots of water in it. We will talk later about more of the physics of why this happens, but the videos clearly show that it does happen. Any other questions on this? Okay, great. So I'm going to go back to the PowerPoint and not play the rest of those videos, I guess, at least not now. So that is the reason that we have these black lines. These black lines tend to be close to the water's edge. That means that the soil is probably saturated. And so these roads are, if you're on them when the earthquake happens, if it's a bridge, bad things might happen. But more importantly, it'll take a really, really long time to rebuild this. In the weeks or months following the earthquake, if you live over here and you want to go visit your family, your friends that live in San Francisco, you're not going to just drive along the interstate and across the bridge like you do now. And you're not going to drive along the interstate this way and across this bridge. And you may not even drive along the interstate this way and across the bridge up in Vallejo. You're also not going to drive along the interstate that way. Right? It's going to be really hard to get there. So transportation becomes a huge issue after an earthquake. So here is a map of predicted ground failure. Liquefaction is this goldish color. You notice that it's all along the edges of San Francisco Bay. And then landslides are in pink. What kind of topography does that follow? Mountains, yeah. Someplace where you've got steep topography. If you have soil that's on top of a hill and you shake the hill, the soil can become dislodged and slide down the hill. So neither are ideal. The landslides, although there's a huge area that is pink in this map, the landslides are less likely than liquefaction. Liquefaction is kind of a thing that we know is going to happen. Landslides are less likely. They're much harder to predict and less likely to cause major damage, but could be a huge deal. Okay, so two types of ground failure. Here's a map that is an estimate, a rough estimate of the ground shaking. So the earthquake starts at the star. This is the earthquake's epicenter, and it ruptures all the way along this line. So what? I guess I should point out first that the different colors obviously are different levels of shaking. The redder or the warmer the color is, the more shaking you get. So this has lots of shaking around here, and this has substantially less shaking, and down here is substantially less than that. So can someone explain to me some component of why the color scale looks like this? Why do we have orange here and yellow here and not yellow there? Why might the ground shaking be stronger here? It is closer to where it originated. Yeah, so that's the number one factor. The energy that's coming out from the earthquake is coming from the cracking, the fracturing of the rocks. And the fracturing of the rocks happen all along this black line. So the closer you are to those fractures, the stronger the shaking is going to be. It's sort of like the closer you are to someone who claps, the louder that clap sounds to you. It's a very similar process. Okay, so why else? This is much farther away from that fracturing than, say, that, but that's a redder color. We talked about that, yeah. Is it because what? Which one is closer to the surface? Okay, so there are mountains that are all along here, and there are mountains that are sort of all along here. Is that? Yes, I was saying because there aren't mountains where the red area is. They're shaking because they're not mountains where the red area is. Okay, so the mountains will decrease the shaking that you feel, right, because you're on bedrock. So you're saying that the type of geology that you are on determines the shaking. Yeah, so that's right. So down here, the reason that the shaking is amplified is the soft sediment idea, the idea that you're not on bedrock, the idea that you're on soft soil, and in addition to just soft soil, this is saturated soft soil. So that is going to amplify the shaking for you. So those are sort of the two main factors. But there's a third factor that this map shows. It's a little bit more subtle, and that is if you look just to the north of this star, and look at that color, and then look at the same distance to the south of the end of the rupture, I claim that this is a little bit redder than that is. Who has an idea of why that might be? Yeah. Is it because the Hayward fault extends all the way downward? So it is possible that will happen. If we assume that this is the only part that ruptures, then the other faults nearby don't matter as much. But it is possible that this rupture could jump to another fault that we don't know about, which would also be bad. But that's not quite the reason at this point. Yeah, next. I think what you are saying is right. Can you expound on that a little bit? Epicenter's way up here. Yeah. So the majority of the energy of the waves, remember the fault is probably 12 kilometers deep. And San Pablo Bay is probably 30 meters deep at its deepest point. So that energy is coming almost straight up. I almost hit myself in the eye with this laser. The energy is coming almost straight up. So the fact that you're not really having any of the energy traveling through water to begin with. Yes, yeah. So this is sort of an analogy that you might have heard in physics class. If you're standing in the BART station, and a train that you don't want to take comes into the BART station, can you think of how that train sounds? It's pretty high-pitched, right? And then as the train, you didn't get on it because you didn't want to take it. The train then leaves the station, and the pitch is lower. Often, the analogy is also police cars or ambulances or trains or airplanes or what have you. It's the Doppler effect, right? You guys know the Doppler effect? So here's a brief idea of what the Doppler effect is. Say we've got, this is the fault, this black line, and this dot represents the propagating rupture. So when I say the propagating rupture, when I say the earthquake starts here and it ruptures that way, this entire black line does not rupture instantaneously. That black line, the cracking rock travels down the fault. I have another YouTube video to show this type of thing. It's in French, but that's okay because we don't need to hear anything. Okay, so this is a concrete column that is under immense pressure, and the concrete column is going to fail. And you'll see cracks form here and then travel all the way down the column. It happens very, very fast, but you will be able to see it rupture. Ready? Here it goes. See the crack start up here and then travel down, sort of like lightning? Was that my computer? I hope not. Okay, so faults work like that also. These ruptures travel at nearly the speed of sound, so it's really hard to watch them, rupture with your own eye. But they do start here, and it would take a number of seconds for the rupture to get from here to down there. The energy is being released from the actual breaking of the rocks. So even though this fault ruptures over the course of the earthquake, energy is not being radiated from the entirety of the fault during the entire duration. The energy is initially radiated from up here, and then these rocks are done moving, and these rocks start breaking. And then energy is radiated from here, and then these rocks are done breaking, and these rocks start breaking, and so on and so forth. And so that's what this represents. This dot is the front of the rupture, and each one of these circles is a seismic wave that is being released from that point. So you can imagine that each black line is where you have an up in the wave, right? Yes? So the question is, why does it start here and go that way and not the other way? We have no idea. It's just luck of the draw. It's luck. It could go the other way, yeah. This is just a scenario quake. We have to imagine that it starts in one place and stops in another, yeah. Yes, in fact, usually, so the question is, do earthquakes ever start in one place and then rupture in two directions? And the answer is usually that is the case. Usually the rupture happens in more than one direction. And there's a movie in like 2 slides that will show actually it rupturing in 2 different directions. Yep. Yes. Okay, so if we were to make a graph of amplitude, that is how big the wave is, versus time for different points relative to this rupturing earthquake, if we were at this little green x, the difference in time between one maximum and the next maximum is something like 1, 2, 3, 4, 5, 6. Okay. And so that would look something like this. Just assume that this green line is for that green x. So if we were to then look at a point that is, say here, we're going to color that blue because, well, the shaking is less intense. The difference in time between the maxima of those waves would be something more like 1, 2, 3, 4, 5. It's slower, right? Compared to the green, which is 1, 2, 3, 4, 5, 6. So that graph is going to look something like this. You take the same amount of energy and you spread it out over a longer period of time. So each individual wave takes longer to pass and is therefore depositing its energy more slowly, and so you feel less shaking. If we have a third x that is right here, it's the same distance, notice, from where the black line begins, from where the propagation begins. So all 3 of these x's are the same distance from the epicenter, which is the same thing as this star. But if we count how quickly the lines cross the red x, I'm not going to be able to do it. 1, 2, 3, 4, 5, 6, 7. It's really fast, right? And so you're taking that energy and smashing it into a really, really small period of time. So this is an extreme example, but how many of you have been on a boat? Any kind of boat. How many of you have felt waves while on this boat, moving up and down? Yeah, they're pretty easy to feel, right? How many of you have felt the tide on a boat? I noticed very few hands. Why don't you feel the tide when you're on a boat? Yeah. Because the change is too slow and you can't register that change in height. That's right. So the idea here is that this red x is experiencing more or less the same change as this blue x, but it's happening over a shorter period of time. It's condensed and therefore more violent. So this is called directivity. It's basically the Doppler effect that's transferred into earthquake science. But the earthquake beginning to rupture here and rupturing to the south means that the people south, in the direction of the rupture propagation, are going to feel more intense shaking than people to the north. So is distance to the epicenter then a very good measure of how strong your shaking is going to be? No, it's not. What's a better measure? Wait. Yeah, so you need to know the directivity, and you need to know the distance from the fault, right? So this is a lot closer. This is a lot farther from the epicenter than this is, but it experiences similar amounts of shaking. And that's because it's more or less the same distance from the rupture fault. It's the same distance from the propagating energy. The epicenter just tells you where the earthquake started. So are there any questions about directivity? I think Professor Allen will cover it again. He doesn't usually cover it at this point in the lecture, but I usually do, so I decided to anyway. Great. Here is a quick video. This is the two-wave propagation. So the earthquake is going to start somewhere around here, and you'll watch the seismic waves propagate away from this source. It's going to happen really fast, so I'll play it a couple of times. Okay, so that's sped up a lot. That's not actually how fast the earthquake would happen. I'll play it one more time, and then I want you to tell me things that you notice. Okay, what do you notice? There seems to be a lot of energy that hangs around up here in San Pablo Bay. Yeah, that's right. In fact, it hangs around for so long that this video has ended, and you still have sort of a picture of all of this shaking continuing. Yeah. Yeah, so the shaking tends to be oriented sort of in the same direction of the fault, right? You don't have strong shaking that's going that way. If you were to map the strongest shaking, the line that would be the strongest shaking is more or less in the same orientation of the fault. Good. What else?